Welcome to section 15.5. In this section, we will be looking fairly briefly at the concept of surface area and how we can use double integrals to find surface area of an object in 3D. So to find the surface area for a surface with equation z equals f of xy, x and y in the region D, and the partial derivatives with respect to x and y are continuous, then we can find this area by taking the double integral over d of the square root of 1 plus partial z with respect to x squared plus partial z with respect to y squared dA. So this is our formula to find area of a surface, given that the surface is a function of x and y, and that x and y are in some region D for the domain. So we're going to try a couple examples. So find the surface area of the part of the surface z equals x squared plus 2y that lies above the triangular region T in the xy plane with vertices 0, 0, 1, 0, and 1, 1. So our region T, as you can see, I've drawn it out over here. So our region T, if I just kind of set this all up here, this is going to be the set of all points xy such that if we're going to integrate this, vertical or horizontal, both are perfectly valid here. We traditionally like to stick with vertical, so we'll have bottom function to top and then set the bounds left and right for the constants. So we're going to have x going from 0 to 1 and y going from 0 up to this line, which is just the line y equals x. So y goes from 0 up to y equals x. So just x there. So our surface area is going to be double integral of the square root of 1 plus, we need to go ahead and get the partial derivatives of this surface, of this function. So partial z with respect to x is just 2x. Partial z with respect to y is just 2. So we're going to get 2x squared, so that's 4x squared plus 2 squared is 4. And then dy dx with y going from 0 to x, x going from 0 to 1. Now, if we look at this innermost integral here, the nice thing about it, if this was being integrated with respect to x, this would be a problem, the fact that we have an x squared inside this radical with nothing else to form a substitution. But this is being integrated with respect to y, which means that everything in here with respect to y is a constant. And the antiderivative of a constant is just the constant again times, in this case, y. So our outer integral is intact. Inside, we just pick up a y, and we get, I'm going to add the 1 and the 4. So we get 4x squared plus 5, evaluated from 0 to x, dx. Then when we go ahead and evaluate, it just turns the y into an x. So now we have single integral, single variable. You can set this up using a u substitution if you like. So you can let u be 4x squared plus 5, and then du will be 8x dx. So you'll pick up a factor of 1/8 and then take the antiderivative as normal, so we get a 1/8. And then the antiderivative of the square root, that's to the 1/2 power. So you add 1 and then divide by that power using the power rule. So we get 2/3 times 4x squared plus 5 to the 3/2, evaluated from 0 to 1. 1/8 and 2/3 makes 1/12. The 1 case, we get 4 plus 5, which is 9 to the 3/2, which is 27, minus the 0 case. In this case, doesn't turn into a 0. It actually turns into a 5 right here. And then we take square root and cube that. So that works out as 5√5, or just 5 to the 3/2 power. So that would be our value. So that is the surface area of this surface, but only the part that lies above this triangular region. Let's take a look at another one. So moving away from triangles, find the area of the part of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. So you can see right here, I went ahead and sketched this. We've got the paraboloid down here in blue. The plane is up here in red, and it just cuts off the top part of the paraboloid. So the part that lies below is just everything down here. So all of that is the area in question. So in order to set this up, we need to look at the region D that is created when we cut off the top of the paraboloid. So I've got this highlighted in orange right here, but hopefully you can see. So if I were to drop this down, it would form something kind of like that, more or less. Obviously my rough sketching is not that great, but we're going to get some region down here. So what is that region? Well, its outer boundary is defined by this cutoff up here. And we can say that the plane intersects the paraboloid in the circle. This is where x squared plus y squared equals z, but z equals 9. So we get x squared plus y squared equals 9. So that's a circle of radius 3. So the surface lies above the disk D, so that would be down here, with center at the origin and radius 3. Okay, so we're integrating under this surface above this region. Okay, and using this particular formula with the square root, we're going to be able to find the area of the blue surface here, everything below that plane. So if we set this up, area is double integral over d of the square root of 1 plus partial of this with respect to x is 2x. So I'm just going to square that, so that's 4x squared. And partial of this with respect to y is 2y. So square that, that's 4y squared. dA. Now we would need to set this up using the region D. This region, because it is circular, doing our traditional vertical or horizontal integration, not the best way to go. In this case, we definitely want to convert to polar. So we're going to convert to polar. so that we can set this up better for ourselves. So we get 1 plus this 4x squared plus 4y squared here. That's the same thing as 4 times x squared plus y squared. And x squared plus y squared in polar is just r squared. Okay, so that simplifies a little bit. And then we get r dr d theta out here. dr, r is going to go from the origin out, and that is a circle of radius 3, right? So r goes from 0 to 3. And theta, we're going around the entire disk. So theta is going to go from 0 to 2 pi. Right. We can go ahead and employ the theta trick here. Because there are no values of theta in this, we can separate the two integrals, and theta is going from 0 to 2 pi. So we just get a 2 pi. Integral from 0 to 3. I'm going to move this r in the front just so that we don't get it confused as like it's in the radical, because it's not. I get 1 plus 4r squared dr. And then this integral now in single variable works out pretty similarly to the one we did in the last problem. We set up a u substitution. We end up, the 2 pi is out there. We get a 1/8 times 2/3 times 1 plus 4r squared to the 3/2, all evaluated from 0 to 3. And again, I'll spare you the nitty-gritty details here, but we get pi over 6 times 37 rad 37 minus 1. So that is the surface area of this blue part of the paraboloid. The 37 rad 37, that's also the same thing as 37 to the 3/2 power. But oftentimes, like the text and the homework and stuff writes it out like this, just so you're aware that that's what that means, and that they are equivalent to each other. Okay, so, but that brings us to the end of section 15.5. That is our, again, brief introduction into the idea of finding surface area using double integrals. When we come back in the upcoming sections, we're going to be looking at the concept of now triple integrals. So we've got a lot of good stuff coming up, and I will talk to you all very soon.